question number 4 for linear algebra from the 2016 examination paper. So we're given a mapping from polynomials of degree 3 into 2 by 2 matrices, and this is the definition of the mapping. And we want to determine t of this polynomial. So this is part A. So t of this polynomial, we use the mapping. So you'll see that the element that goes in row 1, column 1 is the constant coefficient plus the coefficient of x squared. So we take the constant coefficient and add the coefficient of x squared. So 1 plus minus 1 gives us 0. The element in row 1, column 2 is a2 take away a1. So this is a2 take away a1, minus 1 take away another 1 gives you minus 2. The element in row 2, column 1 is 3a3 take away a0. So that'll be 6 take away 1 would give you 5. And you'll notice that the element in row 2, column 2 is always 0. So that's 0. Next we want to determine next we want to determine a non-zero vector such that t of this polynomial gives you 0. So we use our definition of the mapping. So t of here is a general polynomial which gives you this, and we want to choose the coefficients of this polynomial which will give us the matrix 0, 0, 0, 0. So we need a0 plus a2 to be 0, we need a2 minus a1 to be 0, and we need 3a3 minus a0 to be 0. So you'll see that a0 is 1, a1 is 1, a2 is minus 1, and a3 is 1/3 satisfies this condition. So here is an example of a non-zero polynomial which maps to 0. And of course you should all know that t of the zero polynomial would also map to 0. For part B, we want to prove that t, so this mapping, we want to prove that it is indeed a linear transformation. So we take two vectors which belong to P3R. So here is a general polynomial of degree 3, here is another general polynomial of degree 3, and we take alpha is a real number. Now we want to show that t of alpha u plus v is alpha t of u plus t of v. So we take t of alpha u plus v. So here's our alpha, here's the vector u, and here's the vector v. Now you should all know how to perform scalar multiplication for polynomials, and you all know how to add polynomials together. So the new constant is alpha a0 plus b0. The new coefficient of x is alpha a1 plus b1. The new coefficient of x squared is alpha a2 plus b2, and the new coefficient of x cubed is alpha a3 plus b3. So notice we've done scalar multiplication and addition in P3R. And now we want to apply our mapping t to this polynomial. So we take t of this polynomial and we use the definition of the mapping given here. So we're going to end up with a 2 by 2 matrix. The element in row 1, column 1 is the constant plus the coefficient of x squared. So here is our constant, and we add the coefficient of x squared. To get the element in row 1, column 2, we take a2 minus a1. So we take a2, take away a1. To get the element in row 2, column 1, we take 3a3, so we have 3 times this, and then we take away a0, which is here. So that gives us the element in row 2, column 1. And you'll again notice that the element in row 2, column 2 is always 0, so we leave that to 0. And now, this is where we can perform a cheat, because we know we're trying to end up with alpha t of u plus t of v. So if you work backwards, we know that this should equal alpha. Here is our t of u, and here is our t of v. So you can either work backwards or continue forwards. So you can see that we can split this matrix, and we can split it into 2 matrices where we take alpha. So alpha is a factor we can bring in front of the first matrix, and then we can take this second matrix. So you can either work backwards to get the answer, or you can work forwards, whichever you find easiest. And then we've actually proven that t of alpha u plus v is indeed equal to alpha t of u plus t of v, so therefore t is a linear transformation. And this concludes the solutions for question 4.